Hello. Today we will be analyzing this structure by using the direct stiffness method. Okay, in this structure we have no truss members, they are all beam members, a point load and a uniformly distributed load. So let's do the discretization first. This is the first step, remember. So we will assign nodal points and degrees of freedoms and determine the members and so on. So these are the nodal points that we have, and after that the way I look at the structure is as follows. I have a node here, a member, another node, a member, another node, member, another node, and we also have a diagonal member here. This is, let's give some labels: A, B, C, and D. Okay, and I'll show the degrees of freedom on the structure. Now at point A, here fixed support, no degrees of freedoms. So I go to point B, it can move in the horizontal direction, that's my first degrees of freedom. It can move in the vertical direction, second degrees of freedom, and we have a rotational degrees of freedom here. D3, I got D4, D5, and D6. So in this structure I got 6 degrees of freedoms, 4 nodes and 4 members. Okay, now let's determine the members. So I will define my global axis as follows. This is global Y, this is X and Y, and I'll just show it in here. Remember that I assigned the structural degrees of freedom by using the global degrees of freedom. Okay, so this is my first member. I'm defining it from bottom to top, so I show an arrow like that. Okay, that's my second member. I'll define it going from B to C, so B being the start node, C being the end node. Now this is my third member. Its start node is C, end node is D. Let's define it this way. And this is the fourth member. Start node is B, end node is C. So I put an arrow like that. So when I define the members this way, so this will be the local X prime of the first member, this will be the local Y prime. Let's show for every member: X prime, Y prime, X prime, Y prime, and for this one this is X prime and this will be Y prime. Okay, so these are the local axes of every member. Now let's try to determine the rotation angle of every member. Remember that according to our definition, the rotation angle is defined from global X to local X in the counterclockwise direction. So for the first member, that's my global X, and this will be the theta, and that's equal to 90 degrees. So I go every member by member and try to determine the global and local axes. For the second member, the global X and the local X, they are in the same direction, so the rotation angle is equal to 0. So theta for this one is equal to 0. For the third, this is the global X. So I start from the global X going into local X in the counterclockwise direction. So theta will be 270 degrees. And for the third one, again, from global to local counterclockwise direction, and that would be my rotation angle. Okay, now let's show the degrees of freedoms, the local degrees of freedoms of every member. I will just draw another figure. That's the first member, that's the second member, and this will be the third, and this is the fourth member. Okay, so for the first member, the degrees of freedom, the first degrees of freedom will be at the start node in the local X direction. So that's D1, D2, D3, D4, D5, and D6. So here I'm showing the local or the members' degrees of freedom. So these degrees of freedoms are belonging to each member defined in the member's local axis. D1 will be in the local X, D2, local Y, D3, let's show it for every member, D1, D2, D3, D4, D5, D6, D2 will be in the local Y in the third, D4, D5, D6. So here I show all the local degrees of freedom. So what we are going to do while driving the stiffness matrix is to relate these local degrees of freedoms with the global ones. How do we relate them? By using the rotation angle and performing the or rotating or transforming the local stiffness matrix defined in these directions into global directions. But before doing that, let's determine the force vector, and then we'll switch to the stiffness matrix. So I'll just write it here, force vector. Remember that while doing it, we have to do a superposition. This is the structure. I have a uniformly distributed load here, 20 kilonewton meter, and a point load that's equal to 10 kilonewtons. So we are doing a superposition. We are saying that that's equal to no deformation case. We are fixing all the member ends. Let me show it this way. I fix all the member ends, so all the nodal degrees of freedoms are equal to 0. And we have only one member load, and due to the member load, my fixed end moments are and the forces are as follows: 15 kilonewton meter, I got 30 kilonewtons, 30 kilonewtons here. So these are the fixed end forces, and we have plus the only deformation case, and we'll just reverse these forces and show it in here. 30 kilonewtons, 30 kilonewtons. We have a nodal load that's equal to 10. and a moment 15 and another moment here whose magnitude is 15 kilonewton meter. Okay, so the force vector, the unbalanced force vector, let me write it in here, will be a 6 by 1. We have 6 degrees of freedom. So the first force corresponding to our first structural degrees of freedom is 10 kilonewtons. They are in the same direction. So I got 10 here. The second degrees of freedom will be in the vertical direction. I have 30 kilonewtons. They are in the opposite direction, minus 30. The third degrees of freedom will be rotation. And I got 15 kilonewtons moment. They are in the opposite direction. That's minus 15. No force in the fourth degrees of freedom, 0. In the fifth, I got minus 30. And in the sixth, I got 15 kilonewtons. So this is the force vector. And remember that these are all the unbalanced forces at these two nodes. So we are saying that the structure will deform. We will see deformation in these 6 degrees of freedom in such a way that the internal, when you sum up the internal forces at these nodes, they will balance these forces so that the structure will reach to the equilibrium state. And this is the force on the second member when there are no deformation. So the fixed end force vector for the second member, let's use the lowercase as we always do. So fixed end force vector for the second member, I'm just writing it now in the member's local axis directions. So while writing this fixed end force, I will be using these directions. So in the D1 direction, no force, I got 0. D2 is in the upward direction, I got 30 kilonewtons. So this is 30. D3, it's in the counterclockwise direction. I have a counterclockwise moment, 15 kilonewtons here. D4, nothing. D5 is in the upward direction, again 30. And D6 is in the clockwise direction. This is minus 15. So that's the fixed end force vector. And remember, while writing the fixed end force vector, I'm using the local axis of the member. Why? While recovering the member and forces, we always use the local axis of the members, because the forces in this direction will be the axial force, the forces in that direction will be the shear forces, and so on. These are the forces that we will be using in the design. All right, now after that process, I have show all the member and degrees of freedom in their local axis. I calculated all the rotation angles for every member, and I know the fixed end force vector for the whole structure. Now the next step is to determine the structural stiffness matrix. Now here, for every member, I calculated the element stiffness matrix in the member's local axis, the rotation angle by using the rotation matrix by using the rotation angle, and then we obtain the structural stiffness matrix in the local directions. So just to repeat what we are doing here, let me draw the member one more time. So this is our member, and the degrees of freedoms, let me show it in the local directions. This is D1, D2, D3, D4, D6, and this will be in D5. So when we do transformation, we do the rotation, the degrees of freedoms will be converted into the following. D1 will be in the global x direction. at the start node. D2 will be in the global y direction at the start node, and D3 same. D4 global x direction at the end node, D5 global y at the end, and this is D6. So basically, this stiffness matrix is for the degrees of freedoms defined in these directions. When we do the transformation, we obtain the following stiffness matrix, and this stiffness matrix is for this given directions. How do we obtain this one? Let's remember our equation is K is equal to R transpose multiplied with the K at the local directions multiplied by R. So you perform these matrix operations, and at the end you obtain your stiffness matrix. Let's go to the second member. Remember that the rotation angle is the same, but just for completeness, let's show it. D1, D2, D3, D4, D5, and D6. We do transformation, and after the transformation again, since the rotation angle is 0, directions are the same. So this matrix is actually equal to the local stiffness matrix for the second member. Let's go to the third member. I define the third member in this direction. The start node will be at the top, the bottom node will be at the bottom. Okay, so again, this is D1, then this is D2, that will be in the local y direction, D3, D4, D5, D6. Once I do the transformation, this is again our member. So the degrees of freedoms are as follows this time. D1 will be in the global x direction at the start node, D2 global y, D3, D4, D5, and D6. And let's do the same thing for the inclined member. Again, we will show the transformed degrees of freedoms here. That will be D1 local x, D2 local y, D3, D4 local x at the end node, D5, D6. We do the transformation, and after the transformation, D1 will be in the global direction, global x direction at the start node, D2, D3, D4, D5, and D6. So once we do this transformation for every member, we obtain the stiffness coefficients in the global directions. Okay? So let me draw one more time our structure in here. Right? This is our structure. That's the first member, second, third, and the fourth member. And our structural degrees of freedoms are as follows. D1, D2, D3, let me erase this one, D4, D5, and D6. Okay. Now, if you think about it, now let's take a look at the first member. These are the directions and they match the directions of the structural degrees of freedom. Let's take a look at the second member. They match. Third member, they match. They are all in the same direction. And the fourth member, again, they are all in the same direction. So if all the degrees of freedoms are in the same direction, while determining the structural stiffness matrix, you don't really have to worry about showing all the coefficients at the ends of the members, transferring them to the nodes, and writing the equilibrium equations to the nodes, because once all the degrees of freedoms are in the same direction, we just take the coefficient from the global stiffness matrix and add it to the structural stiffness matrix. How do we do that? Let's take a look. There's a practical way of doing it. Now I'm looking at the first member now. The first member, the fourth, fifth, and the sixth degrees of freedom will correspond to first, second, and the third degrees of freedom of the structure. So I'm really interested in the following coefficients. So these three coefficients we don't use them in the structural stiffness matrix, but the fourth coefficients, or the fourth degrees of freedom, is defined as the first degrees of freedom in the structure. So I'm just putting a note to myself. That's D2, that's D3. Again, 1, 2, 3 doesn't have any contribution, but D1, D2, D3. So this actually shows that this portion of the stiffness matrix will have a contribution to the structural stiffness matrix. Why? Let's think about it. Let's say that I want to move this node by 1 degree towards right. How much resistance will I get from the first member? It is D4, and it is that coefficient, that's the force. Okay? I want to move this node by, give a unit displacement in D2 direction. How much resistance will I get from the first member? It's 150. All right. So since this portion of the structure will move, and if you just take a look at the member, it's actually only this node will move, and these are the corresponding stiffness coefficients. Okay. So the second member, let's do the same thing. D1 corresponds to global D1. So that's D1, D2, D3, and I have the same D2, 1, 2, 3, 4, 5, and 6. And from the second member, I will have the contribution to this 6 by 6 matrix. It will directly go into the structural stiffness matrix, right? And again, we can ask the same question. Let's say that I want to move this second, or give a unit displacement in D2 direction. How much resistance will I get from the second member? It is 192. Okay, so this will be fully assembled in, or put in the structural stiffness matrix. Let's continue. Third member, as you see, for the third member, the first, second, and the third degrees of freedom corresponds to 4th, 5th, and 6th degrees of freedoms. So this one corresponds to 4, 2 corresponds to 5, 3 corresponds to 6, and I don't have anything here. Likewise, D4, D5, D6, and no degrees of freedom defined in the structure for the 4th, 5th, and the 6th degrees of freedom. So here, these are the contribution of the third member. These are the resistance provided by the third member to the 4th, 5th, and 6th degrees of freedoms. So as a final step, let's take a look at the fourth member again. For the fourth member, fourth, fifth, and sixth degrees of freedom again corresponds to fourth, fifth, and sixth degrees of freedom of the whole structure. So I don't have any contribution. 1, 2, 3. This is D4, D5, and D6. Nothing, nothing, nothing. D4, D5, and D6. So from the fourth member, these are the contribution. Okay. Now, how do we do the assembly? So let me just write it here. So I'm trying to calculate global K11. Okay. That's equal to. So I'm giving a unit displacement in the D1 direction. How much resistance will I get from the first member? That will be 81. So we got 81 coming from the first member. Continue. What about the second member? So I'm looking at D1, D1. It is that coefficient. In order to move this member by D1 amount, I have to apply, or the resistance coming from the second member is 200. So plus 200, and the third and the fourth member do not show any resistance to translation in D1. So K11 should be equal to 281. Okay. Let's calculate D3 now. Sorry, K13. So let's say that I have a unit translation in the first degrees of freedom, and I want to keep the rotation in the third degrees of freedom equal to 0. How much force do I need for that? So let's take a look at the first member. I'm saying that I want to have a unit translation in D4, and I want to keep D6 equal to 0. How much force do I need? That is 162. Or by just looking at these coefficients, this tells me that this 162 will go to K13. Okay. Let's take a look at the second member. How much force do I need? There's a unit translation in 1. How much force do I need to keep the rotation equal to 0? I'm looking at K13, and that's equal to 0. Plus 0, and that gives me 162. So we do this over and over again for every member. Let's assemble. Let's do K46. Okay. So K46. How much contribution will I get? I'm looking at this row. Okay, there's a unit translation in 4, and I want to keep the rotation equal to 0. K46 is this one, or you can just use this one, doesn't matter. The fourth row, 6th column will give you the resistance of this second member. Let's go to the third member now. Unit translation in 4, keep 6 equal to 0. For this one, unit translation in 1, I want to keep D3 equal to 0. So we have a unit translation, K46, right? So I'm looking at K46. It is 162. That's the contribution coming from the third member. 0 comes from the second member. What about the fourth member? K4, 6, it's this number 82.944 plus 82.944. So this one will give me the K46 as 244.94. Okay, so we repeat this for every coefficient of the stiffness matrix, and at the end of the day, this is our structural stiffness matrix. This is K44, K11, K13. These are the values that we worked on. So you repeat the same procedure and obtain your structural stiffness matrix. We already determined the force vector. Now all we need to do is to calculate the following. K times U is equal to F. You have a 6 by 6 matrix, 6 equations, and once you solve it, you obtain your deformations. Of course, the analysis doesn't end here. We have to recover the member and forces. So let me draw this figure one more time. This is the first member, second, third, and the fourth member. Okay. And our structural degrees of freedoms are as follows: D1, D2, D3, D4, 5, and D6. Now I will write the deformation vector for the first member. So let's show it like that. D1 in global directions is equal to, I need the degrees of freedoms, so let's take a look at it. These are the degrees of freedoms for the first member. Okay, so let me show it also in here. For the first member, we define from bottom to top. That will be D1, D2, D3, D4, D5, and D6. Okay, so how much displacement do I get in the D1 direction? This, I have a fixed support here, so they are all 0. So D1 is 0, D2 is 0, D3 is 0. And what is D4? Is equal to global D1, and that's equal to 0.146. So let's write it. 0.146 is the translation in the fourth direction. How much translation will I get in D5? That will be the second degrees of freedom, second displacement value, which is equal to minus 0.137. So I got minus 0.137. Let me erase this part. Okay. And what about the rotation? I'm looking at D6 is equal to D3 in the structure, and that's equal to minus 0.047. Minus 0.047. Okay, so these are the end displacements. In global directions. Let's do the same thing for the third member. Okay, so let's show its degrees of freedoms. I'm showing them in global directions: D1, D2, D3, D4, D5, and D6. These are the degrees of freedoms in the global directions. So D3 will be then equal to the first 3 degrees of freedom. They are equal to 0 because I have a fixed support here. So let's write down 0, 0, 0. The fourth degrees of freedom is equal to D4, that's 0.116. The fifth degrees of freedom is this one, minus 0.186. And finally, I'll be looking at the rotation at the end, that's equal to D6 in the global, and that gives me minus 0.019. Okay, so we determine the member and forces. Let me do a correction according to our labeling. This should be the fourth member. Sorry for that, that's 3. And this displacement will be equal to D4. Okay, now we determine all the end forces for every member, but remember that these are all defined in the global directions. Now what we need to do is to transform them into local directions. How do we do that? We have to do global to local transformation. Global to local transformation, you can do it this way. I'm showing it. The L1 is the displacements in local directions. That's equal to the rotation matrix of the first member multiplied by the displacements in the global directions. And I have to do the same thing for the fourth member. So the L4 is equal to rotation matrix for the fourth member multiplied by the displacements and displacements in the global directions. So here again, let's repeat. These are the end displacements in the global direction. So for the first member, I'm multiplying this vector with this rotation matrix. And once you do that, you will obtain your displacements in local coordinate system. In local coordinates. Again, let's take a look at this one. I'm multiplying the end displacements in global with the rotation matrix for the fourth member. So in other words, I'm multiplying this vector with the rotation matrix, rotation matrix for the fourth member. In other words, I'm transforming displacement defined in the global into displacements defined in the local directions. And these are the displacements defined in the local directions. Okay, now I have the displacements in the local directions. How can I calculate the member end forces in the local directions? Then F local 1 is equal to K defined in the local directions multiplied by the displacements in local, plus if I have any member end forces, I have to add them. Okay, and for this one, FL4 is equal to K4 prime, this is 1, multiplied by DL4, plus if you have any member loading on it, you just have to add it. So in other words, what I'm doing here, I'm multiplying this one with the stiffness matrix in the local coordinate system. And for the first member, again, I'm multiplying this one with the stiffness matrix in the local coordinate system, and that will give me the end forces. Okay, so let's draw the end forces now. For the member 1, that's the way we defined our member. Okay, so the axial force here is 20.503 in the same direction with D1. Shear force is in the same direction with D2. So this is 4.17 kilonewton. The moment is in the counterclockwise direction. 13.42 kilonewton meters. Now we go to the end node. This is in the opposite direction with the degrees of freedom, direction of D4. So I got 20.503. This one again in the opposite direction with the D5. So it should be in this direction. 4.17 kilonewtons. And the moment is again in the counterclockwise direction. 3.262 kilonewton meters. Let me do the same thing for the fourth member. Member 4. That's the way we define the fourth member. Now remember, all these forces are in the local direction. Okay, so the first force is 9.5 in the direction of the local D1. 9.521 kilonewtons. The second force is in the same direction with D2, which is 6.518 kilonewtons, and we have a counterclockwise moment. The axial force is in the opposite direction with D4, so this is 9.521 kilonewtons. The shear is in the opposite direction with D5, 6.518 kilonewtons, and again I have a counterclockwise moment whose magnitude is 14.64 kilonewton meters. And that's the way we calculate the member end forces. Remember that this direct stiffness method is for the computer applications. Okay, so we define the degrees of freedoms, we define the members, we define the rotation angles. Okay, once we obtain the rotation angles, for every member we repeat the same procedure. We first calculate the element stiffness matrix in the local direction, then calculate the rotation matrix and do the transformation, where K is equal to R transpose multiplied with K prime and then multiplied with R. So we do it for every member, and at the end of the day, for every member we obtain the stiffness matrices in global directions. And then we do mapping, right? We map the local degrees of freedoms with the global, we map the degrees of freedoms in global directions for every member with the degrees of freedoms defined for the structure. This tells us which coefficient will be assembled where in the structural stiffness matrix. And again, we do it for every member. We determine the locations of the stiffness matrix that will be assembled into the structural stiffness matrix. When we say assemble, we are actually getting the coefficient from the element stiffness matrix and add it to the structural stiffness matrix. This process is called the assembly process. Now, when you combine all the element stiffness matrices and you obtain the structural stiffness matrix, I will not go over it, but we know how to determine the structural force matrix, and then we write down the equilibrium equations, which will then be equal to k times unknown displacements is equal to the vector of unbalanced forces. Now, once you solve this system of equations, you obtain the degrees of freedom, the values of the degrees of freedom that belongs to the structure. Now, once we know it, again, this time we go one by one. We visit every member. We determine the end displacements in global direction. So we extract the displacement from this vector and we write the end displacement vectors for every member. And then we do a global to local transformation. We transform these displacements defined in the global directions into displacements defined in the local directions. How do we do that? By just multiplying it with the rotation matrix that we previously calculated. Once we obtain the displacements in the local coordinates, we perform the following operation: multiply the displacements in the local directions with the element stiffness matrix in the local directions, and then add it with the fixed end force vector that will give you the member end forces. And that's the procedure, the full procedure of the direct stiffness method. And we do it, we use computers, and we do the same thing for every structure.